Earlier in this module, I made a video very similar to this one where I examined individual beakers to see if they could make a buffer solution. Now that we know a little bit more about titrations, I now mixed in some beakers that could use a titration to make a buffer. So going through each one of these beakers individually, let's see if we can make a buffer solution. So in this first beaker, we have 1 molar of CH3COOH, which is a weak acid, and 0.5 molar of OH minus, which is a strong base. Now, we cannot right off the bat say that this is not a buffer because this is strong. What we need to do is say this is a titration. So we need to run this reaction to see if our leftover beaker after the reaction has happened is a buffer. So again, just because this is a strong base does not mean it is not a buffer. What we need to do is react it to see what is left over. So what we would do is make an ice table. Remember, OH minus will be the base that we react with this acid. It is a strong base. This will make H2O liquid and CH3COO minus aqueous. So this will be our ice table. So to start off with, we have 1 molarity. We have 0.5 molar. We don't include water. And we have 0 molar to start off with. Now, remember, when we are working with a strong acid or base, like we are in this case, we have a strong base. Remember, this will react to completion with however much of that strong acid or base we have. We can essentially think about this like a limiting reagent type problem. OH minus will be our limiting reagent. It has 0.5 molar and CH3COH has 1 molar. So we are going to run out of our OH minus first. So let's subtract 0.5 molar. And this will react. We'll have nothing left. We will have 0.5 molar left. And in that reaction, we produced 0.5 molar of CH3COO minus, which is the conjugate base. So in this leftover beaker that we could draw, we would have 0.5 molar of CH3COOH, which is a weak acid. We would have nothing strong left. Remember, if you have a strong acid or base in your beaker, it is not a buffer, but we successfully got rid of all of our strong species, and we have 0.5 molar of our weak conjugate base. So this would be a buffer because we would have a weak acid with its conjugate base. The ratio would be 0.5 over 0.5, which is 1, and both of these concentrations fall within 1 times 10 to the negative 3 molar and 1 molar. So this would be a buffer. Now let's look at the second one. We have 1 molar of CH3COO minus, which is a weak base, and 0.5 molar of OH minus. Now, we need to be careful. Just because OH minus is strong doesn't mean it's not going to be a buffer. We need to see if we run this reaction. This is a titration. Remember, a strong base getting put into this beaker. So the thing about this particular beaker, we have a base. Now, to run a titration with this weak base, we would need to add a strong acid to give CH3COO minus a hydrogen to form some conjugate acid to make a buffer. However, we're adding a strong base here. A strong base is not going to help CH3COO minus gain a hydrogen. So this will not be a buffer because when we run this reaction, CH3COO minus is not going to be able to react with the strong acid it needs to produce its conjugate acid. Instead, we made a mistake. We added OH minus, which is a strong base. So this is not going to be a buffer. A rule of thumb, a weak acid, adding a strong acid in there is not going to make a buffer, and a weak base adding a strong base is not going to make a buffer. So be careful when it is 2 of the same. So in this case, this is not a titration. This is a beaker from the original video that I made. This is 0.5 of NH3, so this is not a titration. So Remember, when you don't have the conjugate of the species in your beaker, it is not a buffer. So we have a weak base. What about its conjugate acid, which would be NH4 plus? So in order to make this a buffer, we could add some strong acid in to do a titration and create a buffer. But right now, it is not a buffer. So in this case, we have 1 molar of a weak acid, HClO. It has this hydrogen right here ready to give away. And we're adding 2 molar of OH minus, which is a strong base. So we have a weak acid and we are titrating it with a strong base. So let's set up an ice table to see in our leftover beaker, will that make a buffer? So we have HClO plus OH minus. It is a strong base, and the acid will want to react with the strongest base. This will give its hydrogen to make H2O liquid, and you will have ClO minus left over. So originally you have 1 molar, 2 molar, and you have nothing of your ClO minus. So remember, when we are dealing with a titration with a strong base, we can treat this like a limiting reagent type problem where it is going to proceed 100% yield. All of the base we have will react. Now, what's interesting about this case is we have more base than we do acid. So what will happen here is actually HClO will run out first. So it will give away all its hydrogens to the base that is available. So we have a plentiful amount of strong base to take a hydrogen away from HClO. So this will be minus 1 molar. It will be left with none. Now 1 out of the 2 molar will react of that OH minus. So this will be minus 1 molar. We'll have 1 molar. And in the meanwhile, we created 1 molar of ClO minus. Now, this will not be a buffer because in our leftover beaker, not only do we have something strong left over in that beaker, which right away makes it not a buffer, we used up all of our weak acid. Now, we created some conjugate base, but we essentially used our acid up. So in order to have a buffer, remember, you need a weak acid in the conjugate base or a weak base in the conjugate acid. So in this case, not only do we have something strong, we used up all of our acid. So in that leftover beaker, we do not have a conjugate pair. So this is not going to be a buffer. So let's continue. We have 0.1 molar of our strong base being added to 1 molar of CH3COOH. So let's see if we run this reaction. Are we going to have a buffer left over? So this is CH3COOH, which is a weak acid, plus OH minus aqueous goes to H2O liquid and CH3COO minus aqueous. Let's do an ice table. So initially we have 1 molar, we have 0.1 molar, we have nothing left of this. Okay, so we don't include water in our ice table. So what is going to happen here? Remember, we are working with something strong. We are going to react OH minus the 0.1. It is our limiting reagent. There is less of it, so it will all get used up. Minus 0.1 molar. Now CH3COH, remember, there's 1 molar, and it wants to give its hydrogen to OH minus, but there's only 0.1 molar of OH minus to accept its hydrogen. So it will only react what it can. It will react 0.1 molar. This will be 0.9 molar. This will be 0 molar. And in the meanwhile, we created 0.1 molar. So what's good is we used up all of our strong species because a buffer cannot have anything strong in it. So that's good. Now we just need to see, do we have the correct ratio to make this a buffer? Because we have now created a situation where we have a weak acid and its conjugate. So let's see if rule number 2 checks out. So the ratio of base to acid is going to be 0.1 over 0.9. which is equal to 0.111, which is in the range of 0.1 to 10. So this is a buffer. So moving on, we have 1 molar of HClO, which is a weak acid, and 0.1 molar of HCl, which is a strong acid. So like we saw before, in this example where we had a base and we added a strong base, we have a weak acid. In order to make a buffer, we would need to titrate this with a strong base to remove this hydrogen to make some conjugate base. However, we made a mistake when we ran this titration and we added a strong acid instead. Mixing an acid with an acid is not going to help us. This is not going to be a buffer. In this case, we have 0.5 molar HA and 0.5 molar A minus. This isn't a titration. This is simply 0.5 molar of a weak acid and its conjugate base. So we know it's weak right here. So that meets the requirement of a buffer. The ratio is going to be 1 to 1. So base to acid will be 0.5 over 0.5, which is 1, which meets our requirement. And both these concentrations satisfy rule number 3 of meeting a buffer. So this is a buffer. And lastly, we have 0.75 molar of CH3COOH and 0.75 molar of OH minus. So this looks like a titration with a weak acid and a strong base. So we can again do an ice table. This is CH3COOH aqueous OH minus. This is going to make water and conjugate base. If we draw an ice table, we can see we have 0.75 molar, 0.75 molar. We never include water. We have nothing of our conjugate base to start with. Now, remember, this is strong, so we can simply do limiting reagent. However, we have an equal amount. So our 0.75 molar of CH3COOH will give away its hydrogen, all of it essentially, to the OH minus. So this will all just react. 0.75, we'll be left with nothing, and we have enough base to accept all the hydrogens. So we'll just react this. Boom. So in the meantime, we created (0.75 molar of the conjugate base. Now, we essentially used up all of our acid. So even though we got rid of our strong species, we used up our weak acid. So in our leftover beaker, even though we created a conjugate, we do not have anything left of our original weak acid. So we cannot call this a buffer. So it's really important to be able to go through and analyze a beaker and say, are we running a titration? Do we have a weak acid and its conjugate base, or a weak base and its conjugate acid? And if we run a titration, what's going to be left over in the beaker? And can that leftover beaker meet the requirements of a buffer?